Hey, I hope you remember this journey. This is a little bit of a review of the process of integration, and this course assumes that you've done some of this in other courses, as we've seen before with calculus. And let's have a look up here. Do you remember here the word integration? What that means? They integrate, make a whole, make us whole, I think. Make us one. Okay, a whole unit there. Integrate, as in English, and the maths language is very consistent with that. Let's just go back and have a look at this journey. Do you remember that in looking at calculus, we were en route to the fundamental theorem, and that involved actually looking at upper and lower area sums. Okay, remember that? The sum of all the rectangles which were above the curve and the sum of all the rectangles below the curve, and looking at that, estimating the area under the curve as somewhere between the upper and lower sums. The actual area was greater than the lower sum and less than the upper sum. Okay, so therefore, do you remember that? And then we said, if we did many rectangles under there, and this is what, a large number, maybe n is 500 little rectangles there. We found that the upper sum and the lower sum approached each other. So the area is somewhere in between that upper and lower sum. And we posed the idea that what would happen if that became infinite, the number of rectangles we put under there and did upper and lower sums. So we get to the idea that it would be a complete shaded whole area. Oh, and that's where the word integrate comes from. So here, making it as whole is doing an infinite number of those upper and lower rectangles and looking at the way the area changes. And so come down the bottom here, the journey went down to here, and we said if we took that to the limiting position, n tends to infinity, of what's this? This is the sum from I is naught, the first one, f of x naught, and so that's the height, or the height of the function, isn't it, times a little increment, the width. Okay, let's just have a look back up here. What did we do? We said that's the height of the function f of xi, and this is delta x in here. Okay, so that's a mathematical statement for the sum of an infinite number of rectangles of height f of x and width delta x. Okay, I hope you've seen some of this before. And we use this symbol for it. At this stage, we couldn't work out that infinite sum, but we still had a nice mathematical symbol. We said we go from A to B. Okay, come back over here, up the top here, and we're going from A to B. Then come back down here. Don't get dizzy there. And we're going to, what are we going to do? We're going to sum. That stretched out integral sign is a stretched out S for sum. Did you know that? So that's very commonsensical, isn't it? We're taking an infinite sum, a limit as n tends to infinity of the sum of all of those, and seeing if they tend to something, if they've got a limit, and we're going to do it between the ends where we want the area, and we're going to sum, and this is our notation now. So this sum implies an infinite number of rectangles and summing the areas. It's an infinite number. So this is a very important expression. It's so full of meaning. It's reminiscent of f of x, the height of the rectangle, and dx, delta x. So we use this for an infinite sum. Sorry about that. So there we had a nice symbol, but we didn't know how to work it out at that stage. How can you work out the limit as n tends to infinity of an infinite sum? Oh, because you can't have infinity, can you? All right, so you can't work with that very well. So we went on and said, let's try to do some derivation here. Let's try to come up with a function, a of t, an area function, which allows us to calculate the area from, let's say, some point A to a given point t. I don't know whether you've seen this derivation. I'm not going to do it here, but we said, well, what we're trying to find is an a of t, which represents the sum, infinite sum, remember that's what that stands for, stretched out S, infinite sum, of from A to T of triangles, of height f of x and width delta x, a small increment there. And that delta x is getting smaller and smaller as n tends to infinity. That's what we're after. And here's the big result, right down in the bottom corner here. We found that the derivative of that area function was the original function. What? That's interesting. And that becomes the fundamental theorem of calculus in a minute. I'll show you that. So what it says, if you want the area under the curve there, between the curve and the x-axis for a function, what you've got to do is find the function whose derivative is that. Okay, so the area function has as its derivative this thing. Oh, well, what are you going to do? Well, I guess you've got to undifferentiate it. Okay, if this is going to be a derivative, you've got to come backwards. This is the derivative of A, so we want A, we've got to undifferentiate the function. What? Let's have a look at that and see what that means now. And here's a fundamental theorem of calculus. All right, so fundamental theorem of calculus has to do with this integral sign. So if a function is continuous, now continuous means there are no points which is undefined over the interval. We're going from A to B on some interval, and we're going to say if we can antiderivative, not undifferentiate, that's a Huttyism, we want the antiderivative. So we want to find a function whose derivative is the given function. If we can do that, across the interval, the sum of the areas of an infinite number of rectangles will be given by subbing in the end of the interval into our antiderivative minus the first of the interval. Remember, this is our area function here. We tried to find it and we found the area function was the function whose derivative was the function being considered. And then we evaluate. So we've got to find the antiderivative, undifferentiate it, and then sub in those two values and subtract them. Okay, because back up in the original one there I said we weren't going to look at the derivation. We were looking at this area from a given point here to t. And we wanted the a of t function which would give us that. That's what we were looking at. Okay, so you might go back to your other subject there and check that you understand those basic derivations. I'm summarising them here for you so you get a good understanding of what this symbol stands for. You must understand that this is a limit, as n tends to infinity, of the sum of a lot of rectangles with height f of x and width delta x. That's where it's coming from. This is an infinite sum here, infinite sum. But just remember that, because there's going to be some things coming up where you're going to have to appreciate that. And I'm going to do some of those things now. So come down here and let's have a look at a little bit of a summary now. So first of all, please remember that symbol means a sum of an infinite number of rectangles, height there, the function value, times the width, and taking that to infinity. That's what this symbol means. And then we said, can you actually work it out? Yes, you can. You need to find the function whose derivative is a given function. You've got to be able to antidifferentiate it. So we've got to find this. Now, what's the c doing there? Oh, well, let's just check that out. If you were to say, I find a function whose derivative is this, there would be an infinite number of functions, wouldn't there? Excuse me. Because if I differentiate this to go back to my function, the derivative of c is 0. So you could have many functions, all just differing by a constant, which when differentiated would give the original function. So with our antiderivative, we must remember to say there could be a whole number, an infinite number of functions, all differing by a constant, because the derivative of a constant with respect to x is 0. Okay, so and then the fundamental theorem, just summarising it, says if you want to do that across an interval, you find the area given function, the function whose derivative is the original function, and you sub it in at b and take away a. So here, this could be a and this could be b. the area here would be the integral from 1 to 2 of f of x dx, which would be the antiderivative of this, which is whatever function it is, sub 2 into it minus 1. We don't need c here, because both f there and f there would have c, and when we take them away, we would find there is no c here. So this, we give this a tick. This would work for this function, wouldn't it? We'd be constructing rectangles of height f of x by delta x and taking an infinite sum of those rectangles area across that interval 1 to 2. That'd work. Hang on, but let's have a look. Let's go a little bit further here. But what if, what about this? What if some of it dipped below the axis? What would actually happen? Now, could we just do an infinite sum across 1 to 7, integral from 1 to 7 of our f of x? What would that do? Just remember, this means sum, the stretched out s sign, and it's an infinite sum, limit as n tends to infinity of all of these. Here it is, come down here. That's what it means. And it does fall over here, doesn't it? Can you see why? Well, let's start at 1. Let's do our heights, f of xi, by delta x. Yep. Okay, we'll go across there. That's okay. Now, let's keep summing. But we've got to sum according to this. The height of the rectangle is negative. F of xi, we can still do it. We'll multiply that by delta x. But f of xi has gone negative. Oh, that's a problem. So when we take our infinite sum here, which is our process, a fundamental theorem of calculus, we've got to remember that watch out for the height of f of xi. What about that? It's got to be positive if this is going to mean an area. If it dips below, this won't work, because that would be negatives there, and then we're back to positives here. So that'll be a positive, that'll be a positive, and in the process we would be adding on a product here, f of xi by delta x, which would be negative. Wow, we've got to be careful about that one. So just remember what this is doing here. This is an infinite sum of f of xi times delta x. And it doesn't know, this little sign doesn't know whether f of xi goes negative. So the fundamental theorem of calculus is good, but it won't always mean the area. We've got to watch what this little dude here is doing, the height of the rectangles. Do you get it? It's going to be very important later on, to when we apply this, to see those ideas. So they're fairly simple, but get your head around that. Okay, let's go down, and what's our job now? Well, quite clearly, if we're going to find the area and stuff, we need to find the antiderivative. Don't really like that word much, but here it is. A function which, when differentiated, gives the original function. Just remember why. Because we were looking for an area function from a to t, and we found, and go to your other subject and check you can do this, that area function was a function such that its derivative was f of x. I should put a here, a of t, a dash x, if I'm going to do that. So it was equal to f of x. So we had to find the antiderivative, or the function which, when differentiated, gives our original function. So if we have a function, here we have some, what function which, when differentiated, gives it? Oh, we've got to reverse the x to the n rule. It would have been kx. And remember, because the derivative of a constant is 0, there's a whole family of them. X to the n. What will we do? Increase the power by 1, divide by the new power. Because, just remember, don't get confused now, derivative of x to the n is nx n minus 1. To go backwards to x to the n, what would you do? Let's just check it out. X, nx will increase the power by 1. That would give us n. But then we have to divide by that new power, wouldn't we? So just check that. That's all we're doing. We're going backwards. Why? Because that area given function has as its derivative the function that we're looking at. Okay, so we want to find the function whose derivative is that f of x. Okay, so we're going backwards. That fools you, doesn't it? Okay, so here, what function which when differentiated gives 1 on x? It's ln x. But ln is only defined for positive values, so we're going to make it mod x, or absolute value of x. And again, plus c. Let's just check one out here now. Let's do one. What about integral of x cubed? Okay, so we're going to go x to the 4 on 4 plus increase the power by 1 divided by new power, not timesing, we're going to do all the steps opposite, plus c. And if you checked it, let's check here, x to the 4th on 4 plus c, differentiating that, it would be 4x cubed, still got the 4 underneath, plus 0. Oh yes, it checks, because derivative of a constant is 0. So it could be 3, 4, 5, any number there. So there's a whole family whose derivative gives you that original function. What about e to the x? Well, we know derivative of e to x is itself. So reversing it is just itself. That's an easy one. Ooh, what when differentiated gives cos? It's sine. What when differentiated gives sine? Well, cos gives minus sine. So you would need neg cos to give plus sine. So the way I get students to remember this one is that sine is friendly on differentiation. Let's see what I mean. The derivative of sine is just cos. The one that you've got to watch on differentiation is the derivative of cos, which is neg sine. So going backwards, the integral of cos is friendly, you don't have any negative, but the integral of sine is the one that you've got to watch the negative for. Okay, so I don't know whether you want to use that. The idea when differentiating, you don't have to worry about negative with sine, that's friendly. The derivative of cos is neg sine. And then integrating, cos is friendly, no negative, but the integral of sine is neg cos. Wow, how's your head? Going backwards and forwards, is it spinning yet? You'll get used to it. And the integral of sec squared, what function which when differentiated gives sec squared, is tan x. Okay, so I'm using the word integral here, okay, because it's going to be part of that process, but it's really finding the reverse of the derivative, the antiderivative. Come down and let's have a go. Okay, so here we are. We've got some rules. So if you're finding this reverse process with a sum or difference of two functions, you've got to split it up. You do the first plus or minus the second. I wonder if you see the roots of the proof for that. It comes from the limit, the fundamental definition of the derivative, isn't it? Limit as delta x tends to naught of delta y on delta x, or f of x. So this is the idea of limit as h tends to naught of f of x plus h, take f of x on h. So here, if you added other functions on, you could split the limits, couldn't you? And if you had a constant here out the front of each one, you could take that right out the front. So the derivative and also the integral of a constant times a function is just the constant times the derivative, or constant times the integral. So you can put this out the front. So the roots of that, those rules come from the first principles definition and what you can do with terms there in relating them to their derivatives and therefore to their integrals. All right, so allow us to split functions up. Let's have a look at some examples and see what we can do. Integrate with respect to x. Okay, find that antiderivative here. And we're not doing anything with it. We're not evaluating it over an interval, so we're not finding an area as such. We're just gearing up so that we can. So we're just finding the antiderivative, and then we're going to do this sort of thing. Integral from 1 to 2 of 2 sine x take cos x dx, and we'll see, does that mean area? That's where it's coming from. Well, the fundamental theorem is later on. We're just gearing up to, can you do it? Can you integrate this function? So let's do the first part, the integral of 2 sine x. 2 stays out the front from what we said. Integral of sine is unfriendly. You've got to remember to put that neg in, neg cos. take integral of cos is friendly, so it's take sine x, and don't forget the c, because any function with a little constant down the end, when differentiated, will still give you the same answer there. Derivative of constant is 0. So we've got this thing. Okay. And then what about this one? Sec squared looks a bit unfriendly, all these things here. Let's go through them. What function differentiated gives sec squared? Tan. And it's just a constant out the front. And then neg 2x, oh, that's neg 2 times 1 on x, isn't it? So it's what function which when differentiated gives 1 on x. Can't reverse the x to the n rule there. You could try it. You could try it if you forget. But if you try to reverse this, increase the power by 1, that'd be 0. Oh, so you know you're in trouble there. And then you might think, oh, I remember 1 on x is obtained by differentiating ln mod x. And the 2 is just a constant out the front. Okay, see how I put it there? Well, the neg 2. This one is x to the n rule. Increase the power by 1 divided by the new power, plus your constant. Okay, and then we just state the answer here with dividing by 3 over 2, invert and multiply, so it becomes 2 over 3. All right, do you get it? Just got to go forwards and backwards. Just be watchful now in tests and stuff. Which way are you going? Okay, so 7D1, you need to do all of these to get the process, and I think the setting out is important. The setting out. Now, we're not using the fundamental theorem of calculus. We're en route to it, but we're going to say the integral sine x take 2 dx. Okay, so we're saying, can we find a function whose derivative is this? So we've got to undifferentiate that. Okay, or it's called integrating, isn't it? Just remember all that beautiful language here and symbolising it. That's a sum, a stretched out s, and it's an infinite sum, and that's what we're going to do eventually with a fundamental theorem and relate it to areas. All right, have a go at all those. Don't forget the c's. Plus c. There's a family of functions, all differing by a constant, who would have the same derivative, because derivative of a constant is 0. All right, have a go, and I'll show you the answers now. All right, so there we are. Make sure you got your c's on the end there, because there's a mark. You'll lose a mark if you haven't got plus c. Very important concept there. Derivative of a constant is 0. All right, let's move on and see how you're going. Some screen clippings here from Hayes and Harris publications, so you should have their book handy by. So here, the derivative of x sine x, and let's differentiate it, and hence deduce. Well, why are they doing that? Well, I don't know a function whose derivative is x cos x, because that's a product, and the product rule gives a more complicated answer than that, doesn't it? The derivative, using the product rule, is u dash v, take uv dashed, plus uv dash, sorry. That's the product rule. Now, that's only part of it, so I can't see how to reverse that. So products have to be looked at carefully. Here, what they're feeding us is the fact that when you differentiate x sine x, derivative of the first one is 1, second unchanged, plus the first unchanged, derivative of the second. That's what we're doing here. So it gives sine x plus x cos x. Ah, well, that matches with this. So let's integrate this side. The integral of that would be now here, the integral of our sine x here, sine x plus x cos x, is what? It's x sine x. Okay, we've shown that that's a derivative. Coming backwards, the function there is x sine x when differentiating, plus c, call it c1 here, and therefore the integral of sine x plus x cos x is this, and therefore if we integrate sine x, we've got neg cos x plus a constant, another constant, so you can't use c, it could be a different constant. Okay, so we have to use c2 here, plus that integral is that. So then we can move this across the other side, and we've got plus cos x there. And just use a simple c, which is the c1 take c2, if you like, as you move those terms across. Get the idea? So you can manoeuvre around and try to find the integral of a function which is a product or not clearly got a antiderivative by if you know something about the derivative of an associated function, if you like, which contains that as part of it. Okay, so look out for that. We need to use that idea sometimes. Okay, let's go down to another example. Again, one where they feed us. Hey, what would that be? We can't do that at the moment. Might be able to do that later on. But at the moment, we don't know how to do that. But if we look at the derivative of 1 on sine x, they're giving us a clue here, which is sine x to the neg 1. So therefore, the derivative of that is neg sine x to neg 2, multiplying by the derivative of sine is cos. Oh, they have fed us a nice one. Basically, they've fed us a function whose derivative is almost exactly that. So therefore, when we say what is the integral of this, it's 1 on sine x plus c1. And therefore, and now multiplying both sides by neg 1, it's neg 1 on sine x take c1 if you like. And then we can say 1 on sine is cosec. So this is neg cosec x, and we generally don't put negatives, just so call it c, where c is the negative of c1. Okay, so this sort of manipulation, just showing the relationship of going backwards from here to there, and then deducing, without the negative in there, what our integral would have been. So we're trying to associate what looks to be a really difficult integral here with a function whose derivative is close to it. Okay. All right, so come down. I might get you to do some now in question 3. Okay, so these are feeding ones where you really would have a lot of difficulty finding the function whose derivative is that, but they feed us and they give us a function whose derivative is almost that, and they want us to adjust it. Okay, so have a go at that, particularly down here for the harder looking ones. They aren't hard, you've just got to be careful with your rules there. And here, of course, you've got the quotient rule, and you see some of that over here. Okay, well, let's have a look now at the answers to those. And be careful with your setting out. It's very, very important to distinguish between when you're differentiating and when you're integrating. Okay, so there's down to D there. I'll just come down, E and part of F. Let's go to the rest of F now. All right, so how are you going with that? Let's have a look at one more example and then some more for you to do. Okay, find f of x given that the derivative is this, okay, and f of 0 equals 4. Why have they put that? Let's have a look. We know the derivative is this, okay, so changing it to a power. So what was the original function? The original function, we have to find the antiderivative or the integral. So the integral of this and this we want now. So here we are, put the constant out the front. The integral of sine, the function which when differentiated gives sine, is minus cos. The integral of x to the half, increase the power by 1, that's 3 over 2, divide by the new power. Okay, so just remember a half plus 1, 1 is 2 over 2, so that's 3 over 2, thinking like that. Okay, so here, neg 2 cos x, take 2/3 x to 3 over 2 plus c. But now we're given an initial condition. When x is 0, sub it in, neg 2 cos 0, take 0 plus c. So we can actually evaluate c. Cos of 0 is 1, so 4 equals neg 2 plus c, c is 6. So we actually can find a unique function here. It's a unique function because the initial condition is specified. So that enables us to evaluate the constant in that particular case. Okay, so time for you to try some now. Okay, so here, watch the setting out. we want f of x, so you'll say f of x is the integral of f dashed x, coming backwards, okay, antiderivative if you like, and therefore you'll set it out with this is the integral of x squared take 4 cos x dx, and go through the steps and evaluate c at the end. All right, have a go, and we've come to the end now, so I'll give you the solutions down below here. There we have them. Okay, just remembering now, don't forget to evaluate c, because they have given us that initial condition or a condition on the function, so it provides a unique one. Well, you might have to think about all of this and review your integration processes from other subjects or fundamental ideas there. And we'll be doing this for a while and investigating the use of the fundamental theorem of calculus. And so good luck with that. Cheers for now.